Hello, welcome to a new video of differential equations. Today we are going to be working with a very important concept which is known as the green function. We have already made a video in this channel introducing an example of finding the green function associated to a particular differential equation. So this green function is going to be important because it's a tool that will help us to find the solution for differential equations that are of the next form. We will have a linear differential operator that we will call L, and it will be applied to the function u of x, and this is going to be equal to, let's say, a function f of x. Okay, so as I mentioned, this is a differential equation of a linear operator, a differential linear operator L, right? So for example, this can be representing a differential equation of the form the second derivative with respect to x of u of x plus k squared times u of x equals f of x. So as we can see, this is a linear or second order differential equation that is non-homogeneous. Okay, so every equation that has this structure can be solved by using the green function that we are about to introduce. Another example is that L can be, for example, the third derivative with respect to x and then plus a constant maybe, or maybe L can be defined as the second derivative with respect to x plus the derivative with respect to x plus another constant. These are just two examples of what form can L have. Okay? Perfect. So just in general, we are going to write these kind of differential equations in this way. Okay, so what it is important is that for every differential equation of this form, we are going to have associated a green function, and this function is going to be defined on a subset of R2, because this function, the green function, is going to be a function of two variables, in this case, x prime and x. Okay, so we are going to say that this function is defined in D, which is a subset of R2, and then it must hold that another differential linear operator B applied to G will be equal to 0, where this is going to be for the boundary conditions. Okay, this condition must hold in D, which is the frontier of the set D. Okay, again, B is also a linear differential operator. But the thing here is that associated to the differential equation that we have here, I said that we are going to have a green function that is going to satisfy the next relation. We are going to apply the same linear differential operator to the green function so that we are going to get the Dirac delta like this. So this is the equation that defines the green function. Okay. So the thing here is that we define a new function of two variables associated to a particular differential equation of this form, and that function that we define must satisfy this relation. Okay, so what is going to be important is that with this definition, we are going to be able to show that we can express the solution to the differential equation in terms of this green function. Okay, so we are actually going to propose that solution, and we'll show that that form is a solution of the differential equation. So actually, this can be seen as a theorem, right? So the theorem will say, if we have this differential equation, we can associate a green function that satisfies this other differential equation that also satisfies these boundary conditions. And then the solution to the first differential equation is going to be of the form u of x equals the integral on the region where the green function is defined of the green function that multiplies f of x prime dx prime. Notice this very important fact that we are including the function that we have here for the differential equation for it not to be homogeneous, right? So the solution to the differential equation includes the green function and the element of the element that makes the differential equation not homogeneous. Okay, so we need to show that this is a solution to the differential equation. And how are we going to do that? Well, look into the structure of our differential equation. We see that this linear operator is being applied to u. So we are going to do that here. We are going to apply L on both sides of the equation to see that we get L applied to u of x. And then notice something. This is a differential operator that is of the variable x, right? And this integral is of x prime. So that means that in terms of the linear operator L, these two things that I have here are constants, and we can take the operator inside the integral without any problem. So this will be equal to the integral over d of L applied only to the green function x prime like this. And then we have f of x prime dx prime. Okay, perfect. So with this, we are going to use the definition of the green function, right? Well, the relation that defines the green function. We see here that if we apply this operator to g, we get the Dirac delta. So this is going to be the integral over d of the Dirac delta x minus x prime f of x prime dx prime. And as you should know, this is equal to f of x. So what we see here is that L applied to u of x is equal to f of x. So that means that the solution that we proposed, this one over here, is actually true, right? It is the solution to the differential equation. Perfect. So with this, I wanted to conclude this video because I'm about to make a huge video talking about an example of how to use the green function to solve a particular differential equation. And that differential equation is going to be that the second derivative with respect to x of u of x plus k squared u of x equals to f of x, right? Recall that this can be seen as maybe the differential equation associated to a harmonic oscillator with an external force applied, right? So yeah, on the next lesson, we see how to get to the solution using the green function. And thank you so much for watching this lesson.